Okay, recording, now recording. Zachary, I got you, yes. Okay, let's try to share the screen. Okay, so it's working now. For how long, I don't know, but we'll see. I basically rebooted my computer. Sometimes that just does it. All right, so let's try to continue on from where we were. All right, so we're here. I'm already in a 2.5, except I already lost, what, 12 minutes today? So we'll see how it goes. Okay, I'll try to finish everything up to 2.6 by Friday. 2.7 and 2.8 are on something called the derivative. Okay, and those of you who know what the derivative means, you can't use any derivative shortcuts. That'll be for next week. We're still aiming for the test here. Okay, so let's go ahead with where we were. I may have to talk a little bit faster. I had originally planned to give you an in-class assignment, but maybe that's not going to happen either today, but we'll see how it goes. Okay, continuity, page 114. Continuity. Okay, so put this on your next cheat sheet. A function is continuous at a number a if the limit as x approaches a of f of x equals f of a. Okay, it's a two-sided limit. It's equal to the function value. Limit as x approaches a of f of x equals f of a. Okay, it's on the bottom of 114. And what does that mean? Okay, so right here, crudely speaking, if you have a continuous function, you can draw it without lifting up your pencil from the paper, right? This function looks like it's continuous everywhere. You can just draw it smoothly, okay? So why is the function continuous at x equals a? Okay, so when I get real close to a, the left-hand side, their limit as x approaches a of f of x, okay? So the arrow coming from the left and coming from the right, okay? We have a two-sided limit, and it happens to match the function value itself. Okay, that's the right-hand side there. Okay, so if that's true, that's a very formal definition of having a continuous function. Now, frankly, you don't have to do that many homework problems involving that. So it's there, make a note of it. But most of the time, if they give you a graph, just kind of intuitively say, okay, do I have to lift up my pencil from the paper to keep drawing the graph? Okay, so in figure 2, okay, please notice the open circles. Okay, so for figure 2, I would say the function is not continuous or discontinuous at x equals 1, x equals 3, and x equals 5, right? You have the open circle. Okay, so continuous, continuous. I can draw it without lifting up my pencil from the paper, right? And oops, right here, I got to lift up my pencil to keep going. And continuous, continuous. And then at 3, I got to jump up over here. And then continuous, continuous. And then at 5, I got to jump up. And then the rest of the time, it's smooth and continuous. So for figure 2, the function is continuous everywhere except at x equals 1, 3, and 5. Okay. So that's basically it. Okay. So some examples here. Okay, figure 3, I'm on page 116. The function is not continuous, letter A, not continuous at x equals 2. There's a hole there, right? B, looks like the function shoots up toward infinity, okay? And then you got a single dot here. So the function is not continuous at x equals 0. So normally when we talk about continuity and discontinuity, and I'll abbreviate continuous sometimes with CONT, okay? You're talking about the x values, x coordinates, not the y coordinates, okay? So for B, the function is not continuous at x equals 0. Okay. C, the function is not continuous at x equals 2. Okay. D, the step function, looks like you got to jump up at all the integers, right? The greatest integer function, not continuous at 0, 1, 2, 3, 4, and so on. Okay. So continuous, 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 and then not continuous at 1, continuous, continuous, right? Those are the points where you have to lift up your pencil from the paper. Because maybe there's no two-sided limit, okay? Or if the two-sided limit exists, it isn't the same as the function value, like over here, right? For letter C, the two-sided limit does exist, okay? When I approach from the left or from the right, the limit exists, but it isn't the same as the function value, right? Which tells you got to jump down to get to that point over there. Okay. All right, now, most functions that you know of are continuous everywhere they're defined. So on page 117, okay, I wouldn't stress over this too much, but this theorem, number one, if you add two continuous functions, f plus g, it's also continuous. Number two, same if you subtract two continuous functions. Number three, if you multiply a function by a constant, it's still continuous. Number four, if you multiply two continuous functions, it's continuous. Number five, if you divide two continuous functions, as long as you're not dividing by zero, number five, then the function's still continuous. Okay. And most functions that you know of are continuous wherever they're defined. Page 118. Okay. Polynomials are continuous everywhere. When you drew polynomials, they were always smooth, right? Rational functions, polynomial divided by polynomial, are continuous wherever they're defined, okay, on their domain. Okay. So if you have a problem where you're dividing by something, of course, you can't divide by zero. But other than that, a rational function, okay, polynomial divided by polynomial, it's going to be continuous everywhere that it's defined. Okay. And all these functions, you don't really have to write any of these down. You sort of already know these when you graph them. Okay. Polynomial functions, rational functions, root functions, trig functions, inverse trig, exponential, log, they're all continuous wherever they're defined. Okay. So you draw the exponential function, it was smooth everywhere. You could draw the whole thing without lifting up your pencil from the paper, right? Same for sine and cosine and tan. They were all continuous wherever they were defined. Okay. Okay. Okay, on page 122, you have something called the intermediate value theorem. I'll get to that. Those are the last problems at the end, but I won't talk about it now. Okay, but those are just, I think, the last four problems from the homework. But I do want to get started with some of the homework problems that we have here. Okay. All right, so I'll jump right in. 2.5, there's the assignment. Okay, so we'll go to it. I was asked about one problem from last time, which is 2.427. So let me knock that out of the way. Okay, limit as x approaches zero of absolute value of x equals zero. So that one had absolute value inside an absolute value. Okay, so given epsilon greater than zero, find a delta greater than zero such that zero less than absolute value of x minus a, the a was zero, x minus zero less than delta implies absolute value of f of x. So absolute value of x minus the limit zero is less than epsilon. Okay, so here's the key. We already know from last time, if you have an absolute value inside an absolute value, you can just drop this bar there, right? Okay, so basically you have absolute value of x minus zero is less than epsilon. That says the same thing as absolute value of x is less than epsilon, which is the same thing as what you have here. Okay. So yes, I do have this expression equal to this, which means just let delta equal epsilon. Okay, so for the formal proof, zero less than absolute value of x minus zero is less than delta. Okay, I can go straight from there to there, which is what we were trying to prove. Absolute value of x minus zero, right? That's still the same as absolute value of x, and that's less than epsilon. Okay, here's the a, here's the f of x, here's the L, so end of that proof. Okay, so I wanted to show you question 27 for that and get that out of the way. Okay, so now it's already 9:30ish. Let's try to pick up with some of the problems from here. All right, so from the homework, 3 through 8, I'll try to help you with as many evens as possible. So number 4, for the graph of G, state the intervals in which G is continuous. Where is the function continuous? It's actually easier to say where the function is discontinuous. Okay, so from 4, you basically look at the holes and jumps and so on. So number 4, the function is not continuous at, let's see, -2, -1, 0, and 1, right? That's where you have to pick up your pencil from the paper, right? So to write intervals where it's continuous, Well, you just put open intervals everywhere else. So let me show you how you write the answer to number 4. Okay, so I'm going to write it like this. So f is continuous on the open interval from -3 to -2, union -2 to -1, -2 to -1, union -1 to 0, that's here, union 0 to 1, and then union 1 to 3. Okay, I can barely show the book. I know it's not focused so well. I have that. Okay, so again, continuous on the open interval. Okay, technically the function's not continuous right here because it's not continuous from the left. It is continuous from the right. Okay, so if it just says continuous, so between -3 and -2, function's continuous. Union from -2 to -1, union -1 to 0, union 0 to 1, union 1 to 3. Okay, so everywhere in here, you can draw it without lifting up your pencil from the paper. Same thing here. Okay, but the points of discontinuity are -2. You got to lift up your pencil, right? And -1 and 0 and 1. Okay, so that's the idea behind that one. Okay, so that was 4. You do something similar for 3. Okay, 6 and 8. Make up a graph that displays the following. Okay, 6. Discontinuity at -1 and 4. Okay, but continuous from the left at -1 and from the right at 4. Okay, so -1 and 4 discontinuous. Okay, so this is what I drew. -1 and 4 discontinuous. Everywhere else is continuous. Okay, however, number 6 says continuous from the left at -1. That means if I come from the left, I actually do reach the function value. Okay, so if I come from the left, okay, I can keep going and I can put a dot there without lifting up my pencil from the paper. Then I have to lift up my pencil from the paper, right? Okay, and then for the other part, continuous from the right at 4. So when I come from the right side, I can reach the function value at 4 without lifting up my pencil from the paper. Okay, and you say, where's the y coordinate? They don't say, so it can be anywhere. In fact, you notice I didn't even label any y coordinates. It doesn't matter. You do have to get the x coordinates correct. Okay, but here's an example. I mean, this point could be down here. This point could be up by 55 or whatever. Okay, but this is an example of something that works for number 6. Okay, and here's an example of what works for number 8. Okay, so I'll show it to you, and let's see if we can read that. Number 8, neither left nor right continuous, number 8, neither left nor right continuous at -2, continuous only from the left at 2. So number 8, so discontinuities at -2 and 2. And then it said, I can't show it to you, sorry, but neither continuous from either the left or the right at -2. Okay, so there it is. If I come either from the left or the right, okay, I don't have a closed circle. I got to jump somewhere else for a closed circle. Okay, and then it says, number 8, continuous only from the left at 2. So when I come from the left side, I actually can reach the function value without lifting up my pencil from the paper. So here's an example. Dot there, open here, and continue on. Again, where are the y coordinates? It doesn't really matter. You don't have to have it exactly like this, but here is an example of something that would work. Okay, technically you have infinitely many solutions, but this is the essence of what you want for this kind of a problem. Okay, so take a look at that a little bit later for those. Okay, now number 7, I wasn't going to do, but I'll just give you a hint for it. Number 7 says removable discontinuity at 3, a jump discontinuity at 5. Okay, so I'm not going to do it, but I'll just talk about removable discontinuity and jump discontinuity. So what does that mean? Okay, so this is not the answer, but I'll just tell you what it means. Removable discontinuity is something like this. Okay. Can I remove the discontinuity? Yeah, if I just colored up the circle there. It's almost like I can patch the tire. I can just put a patch and it's there. This is called a removable discontinuity. The two-sided limit exists. Okay, this is an example of a jump discontinuity. Okay, there's no way to patch the tire, so to speak. I guess you could say, well, draw a straight line from here to here. Yeah, but it wouldn't be a function anymore. We're only talking about functions. Okay, so this is an example of a jump discontinuity. You can jump either up or down. Okay, here there's no jump. So I can patch the tire, so to speak. I can remove the discontinuity if I just color the circle, right? Then it'll be continuous. Here, there's no way I can patch the tire with just a single point. If I color in this point, it's still not continuous. If I color in this point, it's not continuous. Or if I put a dot anywhere else, it isn't continuous with a single point. Here, you can make it continuous by just coloring the circle there, right? So this is called removable discontinuity. This is a jump discontinuity, okay? All right. All right, so I've sort of given you stuff you need for 4 through 11. Sorry, well, 3 through 8, I meant. Sorry, 3 through 8. Okay, 17 and 23. Explain why the function is discontinuous at the given number A. Sketch the graph of the function. Okay. All right, 17. F of x equals 1 over x plus 2 at A equals -2. Well, you can tell the function is not even defined at -2. So that automatically makes the graph not continuous at -2, right? If the function is not even defined there, how can it be continuous? You have to lift up your paper to cross -2 because you're not allowed to have -2. Okay, and quickly, what's the graph? Okay, recall 1 over x in green looks like that. 1 over x plus 2, you translate 2 units to the left. So if I go 2 units to the left, I have the red. And the asymptote, which used to be the y-axis, is moved over to x equals -2. Okay, so the graph of this function is the red graph. Okay, and f of -2 is not defined. So you have to lift up your paper to keep going, right? And you can tell, you draw this smooth, continuous, then oops, I got to lift up my pencil from the paper to keep drawing the rest of the graph like so. Okay, so f of -2 is not even defined. Okay, and then question number 21, to give you a piecewise defined function. Now, anytime they give me a piecewise defined function, that's a good bet where you might think the function is discontinuous. Okay, so f of x is cosine x for x less than 0, 0 when x equals 0. Don't be scared by this. This is just a dot, 0, 0, the origin, there it is. And 1 minus x squared for x greater than 0. All right, so I draw the cosine function. Do you remember from trig, what's the cosine of 0? Cosine of 0 is 1. Okay, so I have an open circle here, and then I just draw the template of the cosine function right here. Now we're used to having a cosine go over here, but you can just copy and paste it over there. So there's the cosine function for x less than 0. 0, 0, right? So there's a dot there. 1 minus x squared. What does that look like? Parabola opening down. Okay, and what do you get when you plug in 0? 1, so open circle. So where is this function discontinuous? Where do you have to lift up your pencil from the paper? At x equals 0. Because the two-sided limit, though it does exist, the limit from the left as x approaches 0 and the limit from the right as x approaches 0 are both 1. But it does not match the function value at 0, which is 0. Okay, so the limit as x approaches 0 of f of x, which happens to be 1, is not equal to f of 0. Okay, which tells me that's the reason why the function is not continuous at x equals 0. Okay. Now 23. How would you remove the discontinuity of f? In other words, how would you define f of 2 in order to make f continuous at 2? 23. Okay, so this function is not defined at x equals 2, which means it's not continuous at x equals 2. How would you define f of 2 so that the function is continuous? Okay, so it's just a little bit of simple algebra. Factor the top, x minus 2, x plus 1. Cancel these out, and you have x plus 1. But still x is not equal to 2. So again, in algebra 1, we're kind of sloppy when we do this. Okay, and I'm equally as guilty of that, but there's good reason for it. You kind of get tired of keep saying that. Okay, so is this exactly equal to this? Even though you do this in algebra 1, right? You factor, cancel. Technically, these are not the same. Okay, we did this back on day 1. This is not defined at x equals 2. This is defined at x equals 2. So there's a hole at x equals 2. So how can I plug up the hole? It's a removable discontinuity. Well, just look over here. What happens when you plug in 2? You get 3. So to remove the discontinuity, let f of 2 be 2 plus 1 or 3. Okay, so this is the answer. To remove the discontinuity, let f of 2 equal 3. Okay, here's the graph. Okay, this function is exactly the same as this function, except at x equals 2. There's the algebra, right? So again, in algebra 1, when we go from here to here, technically they're not equal because here 2 is not allowed. Here 2 is allowed. So what's the graph of this? It's the same as x plus 1, slope is 1, y-intercept is 1. Go like that, except you punch a hole at x equals 2. Okay, so now how do I plug up the hole? How do I remove the discontinuity? Define f of 2 to be equal to 3. And there it is, that plugged up the hole. Okay. So that's how that one works. Okay, and then some problems involving domain again. Okay, so 25 through 31. The function is continuous at every number in its domain. State the domain. Okay, so 25 to 31, just state the domain. Never mind about, all this other stuff. I can cover all this up. Just state the domain. Okay, we already know, yes, rational functions, root functions, trig functions, they're continuous everywhere in its domain. So just state the domain. So it's pretty much domain questions. 25 should be easy. Okay, can you tell the answer to 25? I only have to look at the denominator. X squared plus 1. When is x squared plus 1 equal to 0? Never, right? It's impossible. So 25, the answer is all real numbers, which you can write as the funny looking R. Okay. And you can use the funny looking R for all real numbers. Okay, so how about something like 27? Okay, 27, I've got a radical and a denominator. So let's take a look at that. (27) Q of x is cube root of x minus 2 divided by x cubed minus 2. Okay, now we know for square roots, the thing underneath has to be greater than or equal to 0. But how about for cube roots? Am I allowed to take the cube root of a negative number? Yes, I am. The cube root of a negative is negative. Cube root of a positive is positive. Cube root of 0 is 0. So no problems for the top. The top causes me no trouble. So does the bottom cause me any trouble? So yes. So I just set x cubed minus 2 to equal to 0. Add 2 to both sides and do the cube root. So x is equal to cube root of 2. So that gets thrown out of the domain. Okay, you're out of here. That's it. So what's the domain? All real numbers minus the set consisting of the cube root of 2. What's the cube root of 2? I don't know. You can punch it in a calculator. 1.26, I think, when I did it last time. Okay, 1.26 blah, 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 times 1.26 times 1. I think that's what it was. Comes out to be about 2. Okay, 29, arc sine. Okay, by the way, arcsine is the same as sine inverse. Okay, so inverse sine in your calculator, it's normally above sine. So sine, inverse sine, cosine, inverse cosine, tangent, inverse tangent. These are the inverse function. It doesn't mean reciprocal. Okay, so this is not cosecant, secant, cotangent, right? Those are the reciprocals. These are inverse trig functions, right? Okay, so domain. Okay, so you might recall from trig, if you don't, you can put this on your cheat sheet. Okay, for arcsine or inverse sine, you can only take arcsine or inverse sine of something between -1 and 1, you might recall. Okay, the arcsine of 1 is pi over 2 because the sine of pi over 2 is 1. Arcsine of -1 from trig was negative pi over 2 because the sine of negative pi over 2, negative 90 degrees is -1. Okay, so the thing behind my finger, that has to be between -1 and 1. Okay, then a little bit of algebra. Subtract 1 from all three of them. -2 less than equal to 2t less than equal to 0. Divide everything by 2. -1 less than equal to t less than equal to 0. So the domain is bracket -1 0 bracket. Okay, the only things that I'm allowed to plug in here are -1 0 and anything between -1 and 0. Okay, so that one was just kind of remembering your trig a little bit, I suppose. Okay. All right. Okay, then 39. Show that the function is continuous on -infinity to infinity. F of x is 1 minus x squared, x is less than or equal to 1, ln x, x is greater than 1. Okay, the only point where you have to even guess that you might have a discontinuity is at x equals 1, right? 1 minus x squared, parabola, that's continuous everywhere, right? ln x, that's continuous everywhere that it's defined, okay? So when you get a piecewise defined function, you just have to really check what happens in this case at x equals 1. Okay. So how do you do that now? Okay. So again, I only have to worry about x equals 1. If x is less than 1, I obey this rule. It's a parabola. It's always continuous. If x is bigger than 1, I have ln. That's always continuous. So what happens right at 1? So I need to see if the limit as x approaches 1 of f of x equals f of 1. So this is one of the few problems where you're actually using that definition that I showed you at the beginning. Again, you didn't have that many, but this guy, right? Limit as x approaches a of f of x equals f of a, definition 1 at the bottom of page 114. Okay, so that's what I'm using here. All right, so what's f of 1? So you plug in 1 right here. 1 minus 1 is 0. Okay, what's the limit as x approaches 1 from the left? So if I approach 1 from the left, that means I obey this rule. Can you just plug in 1 minus 1 is 0? What's the limit as x approaches 1 coming from the right? So if I come from the right, I obey this rule. Plug in ln 1. ln 1 is 0. Okay, so the limit coming from the left is 0. The limit coming from the right is 0. Okay, that means I do have a two-sided limit, right? You have a two-sided limit if the limit from the left equals the limit from the right, which is 0, and it is equal to the function value at 1. Okay, so therefore the limit as x approaches 1 of f of x is 0, which is the same as f of 1. Okay, so therefore f is continuous everywhere. So we've established that. Okay. All right, 43, they gave me this weird function. Let's see what they want for that. Find the numbers at which f is discontinuous. And if so, is it continuous from the left, from the right, or neither? sketch the graph. It's probably easy to start off with a sketch. So sketch the graph first and go from there. Okay, so you had 41 and 43. I'll do 43. So f of x is x plus 2 if x is less than 0, e to the x between 0 and 1, and then 2 minus x if x is greater than 1. Okay, so let me show you how to do that. Okay, x equals 0, I'll get 2, but since you don't have the line underneath it, open circle. This is linear, straight line, slope of 1. So there it is. E to the x, you know it's an increasing function, including 0, including 1. So I just plug in. What do you get when you plug in 0? E to the 0 is 1, so 0, comma 1. What do you get when you plug in 1? Oh, e to the 1, which is e. E is like 2.7, so a little bit lower than 3. Okay, so there's that middle part, 1, comma e. Line underneath means closed circle, closed circle. And then open circle for x equals 1 here, put in 1 here, you get 1. So 1, 1 is an open circle. Slope is -1, so it goes like that. So there's the graph. Okay, so where is the function discontinuous at x equals 0? X equals 1, pretty clearly, right? Then it talks about continuity from each direction. Okay, so at x equals 0, it is continuous coming from the right. Okay, x equals 0, continuous from the right. If I come from the right side, 0.1, 0.01, 0.001, I do reach f of 0. I do touch 0, 1. So continuous from the right. And then at x equals 1, continuous from the left. Okay, so not continuous at x equals 1, but it is continuous from the left side. So if I come from the side that's smaller than 1, 0.9, 0.99, 0.991, okay, I can actually touch f of 1 without lifting up my pencil from the paper. Okay, so that's what they want for that particular one. All right. Okay, I think I'll stop there. I've got 5 minutes left. I didn't quite get everything I wanted to. I'm short by maybe 2 problems, but I can save it for tomorrow. Okay, I think we're still going to be okay with that. Since my goal was to at least finish 2.6 by Friday, so I think we'll be able to do that. Okay, so I'll give you something to do in class right now. It's not that hard, I hope, just to give you the idea of continuous and discontinuous. So get your cell phones out or do a screenshot if you wish. Let me see if I can find it here. And this should be very easy, I hope. Okay, so all you got to do is give me the x coordinates where f is discontinuous. Okay, so here's the graph. Again, discontinuous means that's where I have to lift up my pencil from the paper. Okay, so where is the function discontinuous? So x equals blah, 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 whatever. Okay, I'll hold this for another 15, 20 seconds. See, some of you have already answered it, then you can just leave. Okay, so take a picture on your cell phone. I'll make it disappear in another 10 seconds or so. So please, if you haven't already done so, take a picture or do a screenshot. Where is the function discontinuous? Where do you have to lift up your pencil from the paper to keep the graph going? So type it in the chat, then you may leave. Okay. All right, I will now assume that you've got it. So I'll make this disappear and I'll close the recording. And that's that, okay.